Okay. All right. So this chapter will investigate the power series representation of analytic functions. Okay. All right. So in the previous recommended homework, I asked you to review the first section of chapter 15, especially in the textbook. And so the subject of the first section is about the convergence tests of infinite series. Okay. And so I will cover several new concepts, which I think that is new for most of you, about dealing with the convergence of infinite series. So the first one is about the upper limit and the lower limit of a real infinite sequence. Okay, so we consider a real infinite sequence an, the index n from 1 to infinity. Okay, which, all right, may converge or not, or diverge. Okay, so it's just an arbitrary sequence. Okay. Now, right? The sequence always has an upper limit, all right? And so we define as here, called the lim sup n goes to infinity of an, and which is defined to be the limit as n goes to infinity of the sup of an for m greater than or equal to n. Okay, and this upper limit, which may be infinite, minus infinite, or any real number. Okay. The reason is that we define an to be the supremum m greater than or equal to n of am. the soup of AM, this is the least upper bound of the set of an plus 1, an plus 2, etc. Okay. And if this set is unbounded above, then this upper bound is defined to be infinity. So this is infinite. If an it's unbounded from in above. Or we say has no upper bounds. Okay. Okay, so maybe it's improper. So this is defined to be infinity if an plus 1, I'm sorry, has no upper bound. Okay, and it is this upper bound of if A1, if an plus 1, has an upper bound. Okay. All right. And if a set of real number has an upper bound, then it has the least upper bound. This is from the completeness of real numbers. Okay. And I think that you already know this fact from calculus. So that this is from the completeness of the set, or just say okay. So this is called so okay, and so an is the essential is the least upper bound of the set starting from an. All right. So we can see that A1 is greater than or equal to A2, etc. So an is decreasing sequence. Okay, so in this decreasing sequence, because that so this is the A sub n plus 1 is this upper bound of from A sub n plus 1. So the set, right? And the reason is that since an plus 1 contain an plus 1, an plus 2. Okay. Right. So this set is bigger than this set, essentially. So the distal upper bound of this set will be greater than or equal to the distal upper bound of this smaller set. Right. So we have that one. Okay. And so the lim sup of an by definition is limit n goes to infinity of an. Okay? So an here. And because an is a decreasing sequence, so the limit of an is equal to minus, okay, if an if an's do not have a lower bound, okay. And it is equal to the greatest lower bound and of A1, A2, etc. If an's have a lower bound. Okay? So lim sup always exists. Okay, so you can see that. Any questions? Okay. All right, so similarly, okay. A real infinite sequence A sub n, and from 1 to infinity, always has a lower limit defined as, so the lower limit is called lim in an, or n goes to infinity, which is defined to be the limit n goes to infinity of the increment where m goes greater than equal to n of am. Okay. And again, the lower limit, which may be minus infinity, or any real number. Okay. Right, and this is because that the Bn, if Bn defined to be the increment of am, for m greater than equal to n, okay, and the increment is actually equal to minus infinity if the set an n plus 1 has no lower bounds. Okay, so if this set starting from an, right, has no lower bounds, then the increment is defined to be minus infinity, and it is, but if this set has a lower bound, then this is equal to the greatest lower bound of an plus 1, etc. If an plus 1 has a lower bound. Okay. Now we can see the lower bound. So B1 is less than equal to B2. So the big B sequence is an increasing sequence. And the reason is that an plus 1, okay, is bigger to plus 1 plus 2. Okay, so this is bigger and this is smaller. Alright? And so the greatest lower bound, okay, the greatest lower bound, right, would be, because you have more possible choices, one more, right? So the greatest lower bound of this set would be less than or equal to the greatest lower bound of this smaller set. Okay, because this set is smaller, so you have this inequality there. So big N Bn sequence is monotone increasing. Okay, so the limit, so that the limit as n goes to infinity of Bn, so that I will write down. So the lower limit, inf, which is the limit of Bn, and it's equal to plus infinity if B1, B2 up to if the set of if the sequence here has no upper bound. Okay, so if has no upper bound, then the inf is positive infinity, and it is the least upper bound of B1, B2, if B1, B2, the sequence has an upper bound. Okay, right. So we have demonstrated that for any real infinite sequence, there always exists the upper limit and the lower limit. Okay, so no matter the sequence, AN sequence converges or diverges. Okay. All right, so let's take several examples. The first one. So let's AN to be minus 1 n here. All right. So this is an alternating sequence. Okay. So we have 1 minus 2, 3. We have minus 1, 2, minus 3, 4, minus 5, 6, etc. Okay. So we have this sequence. Okay. And of course, this is sequence. Okay. AN does not converge. Okay. But we can see that lim sup as n goes to infinity of AN. So you can see the lim sup, the upper limit of the sequence. So as you can see that which is the limit of AN. Okay. But you can see the supplement if you cut. So you see that from okay, the set. So this set, right? This set does not has an upper bound why? Because for the even terms, you have 2, 4, 6, so that the integer go to infinity, right? But for the odd terms, you have integers goes to minus infinity. So this set does not has an upper bound. And no lower bound. Okay? So you see that every an, that's an, the supremum, always infinity, and the Bn, which is the infimum, always minus infinity. So you get, so which is infinity, okay? And the inf, the low bound, minus infinity, which is minus infinity. Okay, so this sequence has upper bound, which is equal to plus infinity, and has the lower bound, which is equal to minus infinity. All right. Second example, we let an to be plus 1 plus 1 over n here. Okay. I.e., so we have minus 1 plus 1 plus 1 plus 1/2 minus 1 1/3 plus 1/4 minus 1, oops, etc. As you can see here. All right, and this sequence, of course, does not converge. Okay? Because it's alternating. But, and since the an, okay, so an is the sup of an. Now, because we want to try to find the least upper bound, right? The supremum. And so we neglect all the negative terms. We look at the positive terms. And the positive terms, as you can see, for the positive terms, is going to, you can see that going down, right? Because it's 1/2, 1/4 is etc. Right? So you can see that if n is even, okay? So if n is even, right? So if n is even, then the supremum or the least upper bound would be 1 over 1 plus 1 over n. Okay? This is the biggest. Because for the others, and then, for example, this term is bigger than this term. Is that correct? Oh, no. is going, this one is bigger than this one. Okay, because this is smaller. Yes, so that is going to equal to, so that is equal to 1. Okay, because they're approaching to 1. So this is going up. So you can see this term is less going up, right? And up to 1. And for all n greater than equal to 1. And for the p sequence, the increment, right? For the greatest lower bound, we look at the minus terms here. And also the minus term, you can see the minus term going up. Okay? So the increment okay, so they're going down, yes. Okay, so they are going down. This one, 1/2. So this is, okay, so this one is smaller than this one. Okay, so this is going down. And so the increment becomes to -1 for all n greater than equal to 1. Okay. Okay. All right. So we take a look. So this is because so for this one, we see 1 over okay, and that they are less than 1, but we're close to 1. And for here, we know, okay, it's greater than -1. Okay. Okay, so that's the upper limit equal to 1, and the lower limit is -1. Okay? So we have these two simple examples. Any questions about the upper limit and lower limits of real infinite sequences. Okay, so now I will state a theorem in my lecture notes. Okay. Point O, or we call the root test. Okay. All right. So, given an infinite series summation n from 1 to infinity of Cn of complex numbers, right? So suppose we are given an infinite series of complex numbers, so C sub n are complex numbers. Then we let alpha to be the lim sup of, right? So we take the nth root of the absolute value of Cn. Okay, so we have so here there's the corresponding real infinite sequence An is what is that An which is okay. So the nth term of the corresponding real infinite sequence An is equal to the nth root of the absolute value of Cn. Okay, the nth root of the absolute value of Cn here. All right, and so this upper limit always exists, right? Always exists here, and because that the An always non-negative, so we know that the alpha can be so that that's alpha. Okay, the numerous things An okay is greater than or equal to 0 for all n. Okay, alpha, the lim sup, must be in from 0 to infinity included. Okay, right. So alpha, this upper limit is greater than or equal to 0, but less than or equal to infinity. Okay, so it can be alpha can be 0 or can be infinite. Okay. Okay. So now, so alpha always exists. In principle, you are able to compute this alpha. Okay, you can compute the alpha. Then, if alpha is less than 1, then the sequence, then the infinite series, right, converges absolutely. Okay? So it converges absolutely. Okay. Which means that not only converges, but also if you take the absolute value of Cn, then this infinite series also converges. Let me see. It means that not only this infinite series converges to a complex number, but also the infinite series of the absolute value of Cn converges to a real number. Of course, it must be a non-negative real number. Okay? So if alpha is less than 1, okay, so this is important. So if the upper limit, okay, of the nth root of the absolute value of the nth terms, okay, alpha is less than 1, then the original infinite series will converge absolutely. Okay, this is the first. The second term, the second conclusion is that if alpha greater than 1, right? So if alpha greater than 1, then this infinite series diverges. Okay. Now, the only case left is alpha equal to 1. Okay. So how about alpha equal to 1? If alpha equal to 1, the test of convergence of the infinite series is inconclusive, which means that we don't know. Okay, so this is called the root test. Okay, this is called the root test. Okay. So the root test is the most the general test we can have. Okay, in mathematics, to test the convergence of an infinite series. Okay. Another mild test we call the ratio test. All right, so consider this ratio test applied to consider an infinite series summation from 1 to infinity of Cn of non-zero complex numbers. So each term in the infinite series is non-zero. Okay. Then, if the lim sup, okay, as n goes to infinity, right, of the ratio, right, of the absolute value of adjacent terms. So you can see, okay, you see here, if the lim sup of the ratio is less than 1, okay, then this infinite series converges absolutely. All right? So that the infinite series will converge to a complex number. And also the infinite series of the absolute value of each term converge to a positive real number. Okay? So if this is true, okay, so the corresponding real infinite sequence an x that an is equal to Cn plus 1 divided by Cn, okay, for all. Okay, so an now is the ratio. That's why it's called the ratio test. Okay, so that is the ratio of the absolute value of the two adjacent terms. Okay, so you can see that. So if the ratio has upper limit which is less than 1, then the original infinite series will converge absolutely. Okay. Now, if there is an integer and if there exists a positive integer, and such that the ratio of the absolute value of two adjacent terms greater than equal to 1 for all n greater than equal to n. Okay? If we discontinue then we know the series diverges. Okay. All right. So for to test that the divergence of an infinite series of complex numbers, we don't have any statement about the upper limit. Okay. Only the convergence test here. Okay. All right. So you see that this theorem is not general than the previous one. So this one is the most general one. Okay. But taking the ratio sometimes is much more easier than to take the nth root of the s value of the nth term. All right. So it depends on the nature of the original infinite series. Okay, depending on the nature of that. So you can select your test. Okay. So these two tests, the root test and the radial test, would be the most general test we can have. And so other tests, all right, other tests can be deduced from these two basic results. Okay. So we take a rest, okay, up to 220, okay. Okay. Alright, so for a more complete coverage of this subject, please see the lecture notes that I have distributed to you, I think before the noon. Alright, so the second section is about a power series. Alright, so power series, a special type of infinite series. Now, we first define a power series. So, given a complex number, say z sub 0, and an infinite sequence Cn, and from 1 to infinity of complex numbers, the infinite series of power function okay, so it's power functions summation n equal to 0 infinity c sub n z minus z0 n's power. Okay, so this is an infinite series of power function because each term is a power function. Okay, so the nth term is nth power of this linear function. Okay. Right. So this infinite series of power functions is called a power series. Okay, about z equal to z sub 0, where z sub 0 is called the center. Okay, and the Cn's are called the coefficients of the power series. Okay. In some case, that without explicitly mentioning the center, a power series will be assumed to have 0 as its center. Okay, so this is an infinite series of functions, and as we know, depending on the value of z, a power series and from 0 to infinity Cn z minus z0 its power may converge or diverge. Okay, So if we if we assign the specific value for z, okay, then this becomes to an infinite series of complex numbers. Okay, this becomes to an infinite series of complex numbers, and so then in that we may ask the convergence of such a infinite series of complex numbers. And of course, in general, it depends on the convergence or divergence of this infinite series, depends on the value of z. Okay, so this is what we want to discuss. Okay, in this section. All right. So now we will give the fundamental theorem, or the most important theorem in this section. Okay. Right. So given a power series and from 0 to infinity, c sub n, z minus z0 to n's power, then we let alpha to be the upper limit of the nth root of the absolute value of the nth coefficient. Okay, so we look at the coefficients, all right, and take the nth root of its absolute value and try to find out the upper limit of alpha. So alpha is here. And of course, alpha always exists, okay? Alpha always exists, and alpha should be in less than greater than equal to 0, but less than or equal to positive infinity, okay? So alpha can be that. So alpha always exists, and alpha is in here between 0 and infinity, and can be 0 or can be positive infinity. Right, now then the power series, okay, summation n from 0 to infinity is Cn, z minus z0, n's power, converges absolutely if z minus z0 has absolute value which is less than 1 over alpha. Okay, and diverge if z minus z0 is greater than 1 over alpha here. Okay, so let's see in the complex plane, all right, and this is z0, okay, all right, and then we find a circle, okay, and the radius here is 1 over alpha. 1 over alpha here. Of course, if alpha is 0, if alpha is 0, then the radius is infinite. So which means that if alpha is 0, then this power series converges absolutely for every z, okay, because the radius is infinite. And when alpha is infinite, then you can see that alpha is infinite. Then this is equal to 0. So for every z which is different from z0, then the power series will diverge. Very strong statement. Okay? Right, in general here. Right, so this is circle divide the complex plane into two regions. Inside this region here, inside this region, for any z inside the circle here, this power series will converge absolutely. But the outside, if z is outside of this circle, then the power series will diverge. Okay? And there is no conclusion for a z on the circle. So if it's on the circle, we don't know. Okay? We have to do it carefully. Okay? When z is on the circle, okay, so that we don't have any conclusive result. And with this, we see the proof here. So now for each choice, okay, of z, okay, the infinite series n from 0 to infinity Cn z minus z0n, right, of complex numbers. Okay? So for each choice, which means that we have assigned a value to z, then this infinite series becomes to an infinite series of complex numbers. So this converges absolutely. Okay? If the lim sup of of the nth root of the nth term, the absolute value of the nth term here. Alright, and we compute what is this? This is equal to z minus z0, okay, and times the lim sup of n goes to infinity, nth root, okay. And this one must be less than 1. So if the lim sup of this quantity this is less than 1, then the infinite series converge absolutely. And diverges if named soup greater than 1. Okay, by the root test. Okay, in theorem 15.1.0. Okay, so we see it's here. But the name soup of this one is alpha by definition, right? So that this statement this is equal only if that z minus z0 is less than 1 over alpha here. Okay? And this statement if only if greater than 1 over alpha. Okay. So we have done. So now the number rho equal to 1 over alpha with alpha is the named soup of the sequence of the s root of the x value of the s coefficients. Okay, this number is called the radius of convergence, called ROC of the power series okay, so that here 1 over alpha, this is called the rho here, all right? So 1 over alpha. All right, so this is the ROC, the radius of convergence of the power series. Okay, so now the following theorem is a consequence of theorem 15.2.a. Okay, so now I state 15.2.1 in the textbook. It consists of 3 statements. So every power series okay, every power series converges at its center. Why? If z is equal to z0, then this is the power series, this is the series of zeros. So this is sum is equal to 0. So of course it converges. Okay? This is trivial. If the power series converges at a point z, which is z1 but not equal to z, the center, then the power series will converges absolutely for every z closer to z0 than z1. i.e. and then z0 is less than z1 minus z0. Okay. So z1 is closer to z0 than z1, right? To z0. You can see that. This is of course true because that if we know that it's at a point, then this point must be on our inside, right? So that the z1, this is z1. Z1 cannot be outside of the circle count because outside of the circle for Z1 the power series will diverge. Okay, so that Z1 is here or Z1 is here. Okay, there are only two possibilities: on the circle or inside the circle. And so, for any z closer than so the distance of z, so inside here, you can see all the z here, also in the convergence region already. Okay, so this of course is true, right? This of course is true. And third one, if the power series diverges, okay, at a point z equal to z2 not equal to z0, then it diverges, okay, for every z farther away from z0 then z2, i.e. z minus z2, z0 greater than z2 minus z0. Okay, so this is a course that if so z2 can only be on the circle. This is z2, or here outside the circle. Okay, so any z further away from z0 then z2 from z0, which means in here. So all z here will diverge. Okay, so the three statement, okay, especially the second and third statement follows from theorem 15.2.8. Okay. All right. Another, the ratio test can be used to determine the radius of convergence of a power series if the limit of let's say the limit and goes to infinity of Cn plus 1 divided by Cn exists. We have to know that limit, not the upper limit, okay? Not the lim sub, it's the limit. So if this limit exists, which is much stronger, okay, then only to consider the upper limit. So this is stated in the second theorem in the textbook. So given a power series with non-zero coefficients. All right, so the Cn's are all non-zero. Assume that the limit alpha, which is limit Cn plus 1 divided by Cn and goes to infinity, exists. Okay, so the limit, not the upper minimum, you should know. The limit, okay, this is much more stronger Okay. So if the limit does not exist, then you can't use this theorem. Okay. But theorem 15.2.8 would be very general. Why? Because upper limit always exists, as we demonstrated before. So alpha always exists, and so we can do the test, all right, easily. Okay, so if the limit exists, then the power series converges absolutely if z minus z0 is less than 1 over alpha and diverges if z minus z0 is greater than 1 over alpha. Okay, so we have the same conclusion here. We have the same conclusion. All right. So I will take a couple of examples. Okay. The ROC of of this power series x infinite. Why? Here, Cn x 1 over n factorial. So now the ratio test will be much more easier. Okay, so, and then Cn plus 1 divided by Cn, absolute value is equal to n plus 1 factorial and n factorial. So this is equal to n plus 1, 1. Okay? So which implies that the limit of the ratio, okay, exists, which is equal to 0, and this is equal to alpha. Okay, so now we have the case that the ratio has limit. Okay, and so we can apply theorem 15.2.2. All right, so that the power series, all right, so this power series converges absolutely for all z in C. Okay, so that rho equal to 1 over alpha, which is infinite. Okay, right. So this power series converges. Okay, for every point z. Okay, so now second, the ROC of 1 to infinity 1 over n Zn, okay, is equal to 1. Okay. For such kind of coefficient, so you can see here Cn is equal to 1 over n, and then Cn plus 1 divided by Cn, okay, which is equal to, and here, okay. And for this ratio, we know that the limit, okay, of go to 1, which is alpha, okay. So that this limit exists, so we can apply theorem 15.2.2, okay, so that ROC equal to 1. Another a more interesting example is here. Find the ROC of the power series summation 1 plus minus 1 s power 1 over 2n and Zn. Okay? So the coefficient is a little bit weird. Okay. And you can see that for such kind of coefficients, the ratio test is not appropriate. Okay. So now we were subject to the root test. All right. So note that 1 over the coefficient Cn is equal to, okay, and as we know, the Cn always greater than or equal to 0. Okay? So never negative. Okay. Right? So that the S root of Cn, which is equal to S root of 1 plus minus 1's nth power 1 over 2n here. And so we will use exponential function and the logarithm, natural logarithm of okay, so that this is equal to exponential function 1 over n and the logarithm of 1 plus, okay. Right? So whenever and since exponential function is monotone increasing continuous function on R. So we have that if we want to find the lim sup of the sequence, right? So this is the lim sup of this exponential function. Okay. Now, because exponential function is continuous, that's the lim sup of the function value will be equal to the exponential function of the lim sup. One over n natural logarithm. Okay. And this property I have write in a theorem by theorem 15.1.I. Okay? Okay. In my lecture notes, so please refer to this theorem. Okay. So we have that one. Okay. So now our focus will be on this sequence. Okay, so this sequence. Now, since an, as we know, defined to be the sup, m goes to n, 1 over m, and the natural logarithm of 1 over minus 1 to n's power plus 2 to the n's power here. Okay. All right, and this one is equal to so now because we want to take this upper bound, okay, and as we know, if m is even, so it started from n there, so that if n is even, we have 1 over n, and natural logarithm 2 plus 1 over 2 to the n's power. Okay. So the leading term will be the biggest term, and this upper bound will be the leading term. Okay, if n is even. But if n is odd, then the next term will be the biggest term. All right. So if n is odd, then the next term 2 plus 2 to the n plus 1's power. If n is odd. Okay? If n is odd. So we have the differences here. Okay, now, but when n goes to infinity, okay, so the lim sup of 1 over n log reason 1 plus minus 1 n's power 1 over 2n here. This is the limit n goes to infinity of an. But we look at the an. If n goes to infinity, this log 2 and 1 over n, so this is goes to 0 here. Okay, so it's easy to see that it go to 0. Okay, so we know that this is alpha, right? So now alpha, so that alpha is equal to the E here and the 0, so it's equal to 1. And so the ROC, rho is 1 over alpha, equal to 1. Okay, so the ROC of this power series is equal to 1. Any questions? Okay. Any questions? Right, so if no questions, then I stop here.